First, let me start by thanking the organizers and the fund, the Fetzer Fund, for making all of this possible. And also thanking all the brave people who stayed all the way to the very end to listen to this. This topic is about entropic dynamics and about some new results for quantum mechanics. First, let me say that, well, I've talked to lots of people over the years, students, collaborators, and they're very, very responsible for educating me on what's going on here. So let's get on to the talk. There are two attitudes about an emergent quantum mechanics. One attitude is centered about the idea that physical models represent nature. Another attitude is centered on the idea that physical models are a framework for processing information about nature. So in this type of situation, the connection between nature and the physical models is a little bit more indirect. In the first case, so of course, I'm gonna go for the second one, okay? Yes, in the first case, an emergent quantum mechanics arises from coarse-graining a model that describes reality at some sub-quantum level. Many assumptions are involved in something like this. You have to specify this sub-quantum model. You have to specify some laws of physics, perhaps action principles. In the second approach, one of the advantages is that the dynamical laws themselves are derived. They are emergent themselves. So principles of least action are derived. Now, it seems we're getting something for free here, but it's not quite true. The thing is that the rules for processing information themselves place constraints on what the laws of physics or the models of physics are going to be like. So the idea is that one does not have to postulate the laws of physics, but one has to be very careful about what those laws or rules for processing information are. One of the features of the first type of model is that you have to decide on coarse graining, what coarse graining techniques you're going to be using. And furthermore, there is a disadvantage here in that the idea is you're going to keep track of lots of microscopic details that sort of get washed out when you do the coarse graining. So there is a fair amount of information that's being sort of wasted here, and so those models can be more complicated. On the other hand, the second type of model focuses directly on the relevant information that happens to survive the coarse graining. These theories are much simpler. I focus on what matters and don't even look at all those irrelevant details that were not important. On the contrary side, there is a problem on having to decide what is the actual relevant information to your problem. You can either use the method of physical intuition, or divine inspiration, or trial and error, mostly error, until you figure out what this is. There is a great advantage to these models that attempt to represent nature. The moment that you have one of those that seems to be working, you have some idea of what that sub-quantum level is. This is sort of allowing you to read the mind of God or something like that. There is an advantage, on the other hand, to the second form, because since we're focusing information on that, focusing our attention on those particular pieces of information that survive the coarse graining, what this is telling us is the following. Once you identify that relevant information, any subquantum theory that provides you with that relevant information is actually an allowed model. So it allows you to constrain what it is that those subquantum level theories might actually be. Very good. Our objective. What we want to do first is derive quantum mechanics as an entropic dynamics. The first part of the talk is going to be a broad overview of things that some of you might have seen before. At the very last part, I'm going to be talking about what's actually new here. So the subject matter. Oh, yes. The objective here is not to discover the Schrödinger equation. Schrödinger did that. What we want to do here is identify what are the variables that are relevant for a problem, and what are the pieces of information, the constraints, that will lead to the Schrödinger equation. So the subject matter. The goal is to predict the positions of particles. Of course, doing just particles is never enough. You really have to do fields to get the whole standard model at least. And so it's either particles or fields or other configuration variables. I'll concentrate on particles. The main assumption is that positions of particles have definite but unknown values. So we have a clear ontology here. The particles have real positions, but these values are unknown. That's what we want to predict. So we're going to have probabilities. So this is a theory that includes both ontic elements and epistemic elements. The wave function will be epistemic. And that is allowed because while the particles have definite positions, they don't have definite momenta. Okay? The momenta are completely epistemic objects. Very good. We'll see that in a second. So here goes. How do we formulate the dynamics? We start with the system being a point in configuration space, which means that unless we do something very, very tricky, the theory is going to be completely non-local from the beginning. We want to figure out what happens or how it is that the system jumps from one state to another. So our goal is first going to be figure out what that transition probability is, the probability of going from x to x prime. And because this is a theory that's information-based, the way we're going to be doing this is we're going to maximize an entropy. We're going to vary this entropy, vary the probability distribution and figure out which one maximizes that. Next thing is we need to know what that prior probability distribution is. And so we would say, a priori, before we know anything, the system could go anywhere. The particle could jump all the way from here to Andromeda. We don't know anything, maximum ignorance. Next step, we say, let us impose now the pieces of information that we consider to be relevant to this problem. The very first one is we're going to assume that whatever these particles are doing, they're following continuous trajectories. What this allows us to do is to analyze a motion over a long distance in terms of motion over short steps. So the assumption that the motion is continuous really is telling me that I only need to analyze what happens for short steps and then accumulate many, many short steps. So how do we impose that the steps be short? Well, we impose that the expected value over that probability distribution of the step be some small quantity. There are n constraints of this, one for each particle. And I'm going to, at some point, I'm going to take the limit of kappa going to 0. So that means that the steps become infinitesimally short. Next, the next piece of information is we do want, and I'm not telling you where this comes from. This is a relevant piece of information that is divine inspiration. The motion of these particles is going to be correlated. And so what I'm going to assume is that there exists a potential, I call it the drift potential, that acts in configuration space. The notation here is that n is the particle, a is the coordinate x, y, z. And when I want to talk about both particle and coordinates in configuration space, I'll use capital letters for the whole index. There is a potential, and this is a single a potential defined in configuration space. There is a single constraint, and that on average, the component of the displacement along the gradient of that potential is some small quantity. It is this guy that's going to eventually morph into the phase of the wave function. It's going to be the action at some point. But right now, it's just a potential. We're done 50% of the way here. It's just a matter of reading what's actually going on. Once you maximize an entropy subject to constraints of this type and of that type, the answer is that the maximal entropy probability distribution is some exponential where there is a Lagrange multiplier for the short step constraints, and there is another Lagrange multiplier alpha prime for the drift potential constraint. And now we can start reading what this means. If you consider, it's a Gaussian, right? You can see it's all quadratic, so it's very simple. A typical displacement will be composed of an expected drift plus a fluctuation. The expected drift is along the gradient of that potential. The fluctuations, of course, by definition, have zero average, and the correlation is something like so. We already see something interesting here, which is that the expected drift goes like 1 over alpha, that Lagrange multiplier that gives you short steps, 1 over alpha, while the fluctuations go like 1 over alpha to the 1/2. What this means is that for very short steps are achieved for large alpha. For very short steps, large alpha, the fluctuations completely dominate the motion. So what we have here is a type of Brownian motion in which the particles have completely well-defined positions, but there is no tangent to the trajectory. It makes no sense to talk about the instantaneous velocity or the instantaneous momentum of these particles. Very good. If we're going to figure out how these short steps accumulate, we need to introduce further tools. The tool that we introduce really to do this is the notion of time. The foundation of time is always in the dynamics. For large alpha, short steps, the dynamics is all in the fluctuations. So let's look at the fluctuations again. I didn't tell you what those short steps were, what those kappas, but I can equivalently tell you what they are in terms of the Lagrange multiplier. So we're going to define the duration between, the amount of time it takes for a step to happen in terms of the alpha, and we're going to define the duration so that the motion looks simple. And I'm just going to say that the alpha, the Lagrange multiplier, is like 1 over delta t. As delta t goes to 0, alpha goes to infinity, steps become infinitely short. Now, this is the alpha for each particle. Different particles are different. So yes, it is true that this guy is proportional to 1 over delta t, but there are some constants there that are particle dependent. Different particles have different c's. So I'm going to rewrite that in terms of other constants, particle dependent constants, that I'm going to call m. And so different particles have different m. And then there is another constant there that just takes care of the units, so that if I measure delta t in seconds, these guys here are units of mass. So if I just substitute this back here, I have this very interesting situation in that time is defined so that the fluctuations increase linearly. This is very much like even in classical mechanics, Newtonian mechanics. You define time in terms of the motion of a free particle. The free particle goes equal distances in equal times. That's the clock. That's the ultimate clock in Newtonian mechanics. Well, in entropic dynamics, the ultimate clock is also the free particle. It's the fluctuations. That's how you measure time. This also shows that mass is something that has to do with fluctuations. It's a measure of how much these particles are fluctuating. Very good. So the basic equation of motion is going to be, if you give me a probability distribution for the initial distribution of the particles, you propagate it with the transition probability that we just computed, you figure out what the probability distribution is the next instant. This is an integral equation. We can rewrite it as a Fokker-Planck equation, which takes the form of a continuity equation, where the velocity that appears here can be written in a form like this, where here we have the mass tensor. If this starts looking to you like the guiding equation in say, a Hamilton-Jacobi formalism, it's because that's precisely what it is, or it will be. And what is that capital phi there? That capital phi, which is what we obtained from here, coming down, figuring it out in this form, that capital phi includes a drift component, and it includes an osmotic component. This is the guy that's going to be the phase of the wave function. We can also see here that the relative effect of alpha prime, the other Lagrange multiplier, will be to enhance this part over that one. That's going to be important. Thank you. So the problem, this is just standard diffusion. It's not quantum mechanics. So how do we fix it? We allow the drift potential to become dynamic. At this point, this drift potential, which has some pre-established externally fixed field, now we're going to allow it to become dynamic, which is an idea introduced by Nelson in 1979, that it is very interesting to consider diffusion processes that are nonetheless non-dissipative. So how do we do that? The clever way to do this is I'm going to introduce a functional of rho and phi, and I want to introduce this functional in such a way that this is the time derivative of rho. I can always do this. I know what the time derivative is. It's given by the Fokker-Planck equation that I just got in the previous slide. So I can always do this, but now you see that I can also integrate and figure out what the h is that its functional derivative gives me this guy. Something like that. Trivial. Easy. There is an integration constant that's going to become crucial in a second. Very good. So we impose this. I never told you that h was an energy. I need not say so, but why not, right? It's conserved. If you do that and impose energy conservation, not only we get the Fokker-Planck equation, but we find that in order to get energy conservation, phi affects rho. But in order to get energy conservation, we have to allow the rho to affect the phi, and so that we have the two evolving as coupled fields. That condition tells me that phi has to satisfy an equation of that type, which, of course, we recognize as Hamilton's equations. This was derived. And from here, you get Poisson brackets, symplectic structure. You can even write down an action. So all of these are emergent properties of these constraints. So here we have entropic dynamics. It's described as a Fokker-Planck equation, a Hamilton-Jacobi equation. And we have to go back to what's going on with this integration constant over there. So I have to give you some form. Different forms of f lead to different forms of dynamics. One possibility is to say that f happens to be linear in rho. If you do that, this is just the classical Hamilton-Jacobi equation. This is a theory in which we're processing information. So I'm going to make a wild assumption here. The wild assumption is that this f will not only depend on an external potential, but it will also depend on informational quantities that ought to appear once to have probabilities. There are two informational quantities that appear there. One of them, and I don't have time to go over this, just because I'm running out of time, right? But one of them is the Fisher information associated to the probability distribution rho. The other one, and this is actually just as trivial, but I don't have to mention it, is the mass tensor itself. The mass tensor in configuration space is also something that comes from information geometry. This quantity, this parameter xi here, is a parameter that tells me how much more, weighs the importance of these terms relative to standard potentials. This is what's going to lead to the quantum potential. And whatever this value is, the theories with negative xi end up being unstable. Xi equals to 0 is essentially the classical Hamilton-Jacobi equation. All the values of xi positive, I'll just call them h squared over 8. So that's the main result. Nothing prevents me from combining rho and phi in this form. And of course, the result is the Schrödinger equation. The Schrödinger equation appears as a convenient way to manipulate these rho and phi that are interacting with each other. So that's the main result. But now, let me point out that this is an equation at the macro level. It's an equation for rho and an equation for phi. So what's going on at the micro level? What's going on at the level of those Brownian fluctuations? Notice also that at this level, the constants alpha prime, the Lagrange multiplier for the drift potential, and that boring constant that just adjusted units have completely dropped out. So let me look at the following symmetry. Look at this. The expected drift and the expected fluctuations have alpha prime here. I can actually, if I consider different theories with different values of alpha prime and different eta, none of that affects the Schrödinger equation. So here we have a theory, a symmetry. I can go ahead and absorb this alpha onto eta, into a new eta prime. This is just very convenient. And if I do that, then alpha prime appears over here. So now look at what's going on. If I change the alpha prime, I can suppress the effect of fluctuations relative to the drift. Or if I increase alpha prime, I can increase the level of the effect of the drift relative to the fluctuations. I have a bunch of microscopic theories with all of them Brownian motions, some with huge fluctuations, some with very little fluctuations, and they all lead to the Schrödinger equation. In particular, for larger alpha prime, the fluctuations can be totally suppressed, and the particles follow smooth trajectories along probability lines. That's what I would like to call the Bohmian limit. So the Bohmian theory is a special case of a broader set of theories. All of these microscopic theories will lead to the same macroscopic Schrödinger equation. Conclusions. Entropic dynamics provides a pathway to Hamiltonian dynamics and action principles. Quantum dynamics is a non-dissipative diffusion in configuration space. The probabilities that I have used here are what people normally would call classical probabilities. There are no quantum probabilities. I don't like looking at it that way. Inference is inference. You introduce probabilities as a tool for reasoning. There is no such thing as quantum probabilities or classical probabilities. There are probabilities for reasoning. But if you think that these probabilities are classical, you might be misled into thinking that this theory is like a classical theory. Not at all. Non-dissipative diffusion in configuration space, this is as quantum as it gets. Final conclusion, there is a family of models. I'm done. There is a family of models that differ at the micro level, all leading to the Schrödinger equation at the macro level. Thank you.